Hello, my name is Riley Orndorff. Today I will be presenting my analysis of a mass spring system oscillating in two dimensions. The purpose of this lab is to examine the complex motion of a mass swing in a 2D arc while simultaneously compressing and stretching on a spring. As a brief preview of our main results, I found that the computational model successfully predicted the primary periods of oscillation for both the x and y components. However, the experimental data exhibits a slight amplitude decay over time that the idealized computer model does not capture, just due to the real-world dissipative forces. Ultimately, the total energy of our isolated system remained perfectly conserved. To model this behavior, we rely on two fundamental physics principles. The first is Newton's second law, or the momentum principle, which states that the change in momentum equals the net force times the change in time. We must use this model because it forces the mass because of the forces on the mass are constantly changing in magnitude and direction as it swings. The net force is a vector sum of the gravitational force, calculated as negative mg in the j hat direction, and the Hooke's law spring force, which is negative k times the stretch s times the unit vector l hat. The second principle is the energy principle. Because we define our system to include the mass, the spring, and the earth, there is no external objects interacting with it, meaning that the net work done by the surroundings is zero. Therefore, the change in total energy must equal zero, where the change in E is the sum of the change in kinetic energy, change in gravitational potential energy, and change in spring potential energy. For the experiment, I utilized the provided video file in Tracker, and the system consists of the mass, spring, and the earth, leaving the surroundings empty. I calibrated the spatial distance using the known length of the spring from the pre-lecture videos and set the origin at the rigid attachment point of the springs. By tracking the center of mass frame by frame, I extracted the changing coordinates. The initial conditions pulled directly from the first frame of my data are an initial position vector of 0.0694, and the y is negative 0.634 meters, and an initial velocity vector of 0.000 meters per second. The physical parameters used include a mass of 0.402 kilograms, a spring stiffness constant K of 6.83 newtons per meter, and a relaxed spring length of L naught, relaxed spring length L naught of 0.123 meters. These parameters were then entered into my GlowScript starter code. I exported the position data as a plain.csv file containing only numerical coordinates to drive the simulation. Inside the calculation loop, I set my time step to a very small interval of 0.09 seconds to ensure the accurate force integration. The code iteratively computes the vector L from the origin of the mass, evaluates instantaneous gravitational and spring forces, updates the velocity and position of the ball using the velocity and position update formulas, and calculates the four energy components at every step to track conservation. When comparing the model predictions to the experimental data, the periods of oscillation align very well, but we observe a slight widening discrepancy in the maximum amplitudes over time. This variance represents our primary source of error. The computational model assumes the idealized scenario, whereas the physical experiment is subject to non-conservative forces like air resistance and internal thermal dissipation within the spring coils, causing the real-world system to lose mechanical energy. Additionally, slight human error in manually clicking the precise center of mass frame by frame in Tracker introduces minor statistical noise into our experimental data plot, as shown here. Now to address the what does it mean question. First, is the energy principle satisfied? Yes, as seen in the energy plot on screen. The orange line represents the change in total energy. It remains pretty much flat at zero throughout the entire runtime. The kinetic energy, gravitational potential, and spring potential energies oscillate violently, but are simply exchanging energy back and forth seamlessly. Second, estimating the oscillation periods from the data yields a period in the x direction of approximately 1.61 seconds and a period in the y direction of approximately 1.52 seconds. These values differ because the x-axis motion is governed strictly by the spring's stiffness and the mass, while the x-axis motion behaves like a pendulum, heavily influenced by the length of the string and gravity. The overlay of these two distinct periods is exactly what produces the complex 2D scribbled trajectory path. And yeah, thank you for watching.